Hello, developers. Let's start developing. Our work of the day will be the fourth task of Advent of Code 2022. And let's read through the assignment first. Space needs to be cleared before the last supplies can be unloaded from the ships. Every section has a unique ID number and each shelf assigned a range of section IDs. Cool. Many of the assignments overlap. Oh, no. Overlapping intervals is one of the least interesting problems ever because it's usually hard to get it exactly right. There is a lot of difference if something is equal or less and the start and the end and everything. So let's see the data. Try to quickly find overlaps and the two duplicate pair up and make a big list of the section assignment for each pairs. Puzzling. Consider the following list of section assignment pairs. Oh, I love this kind of input because that means that we get to parse it. In my case, I prefer to parse data like this using a regex instead of some splits and whatnot. So what we will have? We will have some numbers. No, we will have a beginning and some numbers, and then we have a literal minus sign, and then we will have some more numbers, potentially more than one, and then we have a comma, and that's a literal comma, and then we have this thing once more. Oh, this thing once more, and then we end. And now we need to extract this and this and this and this. So we have four numbers and we need a structure that will hold them. And let's create such a structure. That's an elf pairing, and then we have first one that is an elf, and the second one that is an elf. And what is an elf? Well, we will have start, which is a number, and end, that is a number. So right now we need to parse our input using this exact regex. So we're gonna have input, what we're gonna have. Our input is an array of elf pairs, which means that our test is getting an elf pair, our show input is getting an elf pair, our input is an elf pair, and of course we are returning an elf pair, but we're really not. In order to do that, we're gonna need to map this thing, and for each line we have some code that we're gonna need to write. So first of all, we're gonna need to line dot match on oh on this specific regex. Yep. And if the line matches, this will return something that is called regex match array, and that's I want to call that match. And now we have match of 1, for example. That will be some kind of a value, and so on and so forth. And we're just gonna go and assume that we parsed the input correctly. And speaking of input, Let's have our input. So this is our input. So we're gonna return something that has the first, and the first is something that has a start, which is exactly this. And I think that from now on, CodePilot will be able to guess correctly what we actually want to do. Yep, that one and that one. And yeah, let's put in this in. So now we are returning some input, and I have no idea whether this is working or not. So let's see. This will show us what it will return zeros, but it will show us the input that we have. And since my computer is kind of weird with starting npm when I'm recording anything, I will just need to pause and see. So we have our results. We can see that we have starting and ending in 2 and 4, starting and ending in 6 and 8. Let's see if that is correct. Yeah, that is correct. I'm gonna get the whole inputs as well and test it out with that thing. Let's see what this thing has to say about that. Because quite often we have a situation when something works for regex especially, works for single digit numbers, but because we did something somewhere, it won't really work for multi-digit numbers. Well, the results are in, and we can see that we actually have most of the data correct, if not all. I wasn't able to check everything, but 590, 490, 52, 53, 351. So the data seems correct. So yeah, I'm gonna assume that it is correct, correctly parsed. Now we have our data parsed, and now we need to actually see what the task is. What is the task? For the express alpha has assigned sections, second paired word assigned two sections, yeah. These sections are going to look like this. Yeah, this one only has one, this one has three. So this one 2.8 fully contains 3.7, yes, and yes. How many does one range fully contain the other? Uh-huh. So if we have two ranges, one range can be a strict subset of the other. And by a strict subset, yeah, this is actually quite easy to program out. Is there a catch? I don't think so. The catch is that it might be the any way around. So either the first contains the second or the second contains the first. And I have an inkling what part 2 might be. I'm sometimes wrong, but I'm sometimes right. Let's see the large input, and I want to do something alternative. The correct way to solve this is to analytically guess what the relationship is. In this case, I think the condition that we're looking for, if the start of the first one is less than the second, and the end is less than or equal to the second, and the end is less than or equal to the more than or equal to the second end, and so on and so forth, and that gets kind of complicated. So, and of course, we need to then invert it. But what I want to do an exhaustive map, which will only work if our input is relatively limited. So what I want to do is I want to run some tests. For each elf par, give me the math.maximum of. Actually, I'm gonna give it a few numbers here. EP first start, EP first second. No, I'm not gonna do that. I'm gonna do this instead. All the first start, first end, second end. Of course, the ends are bigger than the starts. And I'm gonna say, give me the maximum number. Log that. I don't need the starts because the ends are always equal or bigger to the starts. So give me the biggest end there is. Let's try that. Because of reasons my console is slow. So I run the test command and it seems that the biggest value that we have is 99. So this means that we can safely say that the maximum is 100 or even 1,000. Who cares? So we're gonna create some kind of a map which will be this. And we're gonna create some kind of a counter, which will be, of course, 0. And now for off, for each elf pair, actually we can deconstruct this immediately, and first and second of input, we can have a map. What will this map do? It will be initially filled with zeros, and from the start until the end, and the end is actually inclusive, let's add 1 to the map. No, I don't want to do that. You know what we're gonna do? We're actually gonna add 1 to the map. So after this finishes, part of our map will have zeros, and part of our map will have ones. Now we're gonna do the same thing for our second elf. And if I do it like this, part of the map will have ones, part of the map will have zeros, and maybe if they have some kind of overlap, part of the map will have twos. That means that they are overlapping, but we're not looking for an overlap. If we looked for an overlap, this would work. We will just need to see, are there any twos in this map? And since it's a relatively limited map, it's only 1,000 elements, that search will be quite fast. But we don't need to find that. We need to find whether one is encompassing the other. In order to do that, I will do this. I will use 2 for the second, which means if they have some kind of an overlap, part of the map will have zeros. Part of the map where only the first one is working will have ones. Part of the map where only the second one is working will have twos. And part of the map when both of them are working will have threes. So, if there is a complete overlap, one goes over the other, that means that there won't be any ones. If the second completely overlaps the first, there won't be only ones. There will be twos and there will be threes. And if the first one overlaps the second, there will only be ones and threes. which means we need to go through the map and see if there are any twos. Any ones is actually we can use the sum operator here, which will directly return me a boolean. Are there any twos? Give me that. So now, if we have ones and twos, that means there is some part where they are not overlapping. But if any of this is false, actually we can go with the other one. No ones. Every x is different from 1. And actually we can have this. If we don't have any ones, we can increment the counter by 1 and we can continue processing. We already finished. We don't need to check whether there are twos. Yeah, and I like this syntax better. Now we're checking if there are any twos. If there are no twos, well, we just increment the counter and we're done either way. And now we just need to return the counter. Again, this is way suboptimal instead of solving this problem analytically. This way we are basically simulating the problem and looking at the result of the simulation. This is efficient only because we have few sections. If we had a million sections, this won't be efficient, but we have about 100. So let's see if this works and if we have only two overlaps. Well, it did something and we got 6, which is definitely not the correct value. So, okay, now we're going to debug. Console log. Well, show me the map. And I'm gonna lighten the map. Let's have it have 20 items. Or 10. 10 is enough. Let's see. Well, we got some result, and looking at them, we don't have an overlap here, so we have ones and twos, 1 and a 3 and a 2, 1 and 3 and 1, twos and threes, ones and threes and twos. So this means that our generation of our map is totally correct, but something is off with our counter. I guess I have no idea how to write ones and twos. No ones. Map every x. Check on the map if every x is different than a 1. It should return false for this one. This x is not different than a 1. So I will remove this part and instead log the no ones. And in case that doesn't work, I'm gonna log the no twos. So we got our results. It means this is false, then we have a true, we have a false and a true, we have a false and a true for the third case, we have a false and a true for the fifth case, and we have just a true for the fourth case, and then we have a false and a true for the fifth case. Which means that this thing always returns true because there are some that are not equal to 2. I changed one of the sum to an every, but I didn't change the second one. So let's try it once more. And this shows the importance of testing with a small set of data. Otherwise, I would have been debugging this quite a while. Let's run it once more. And now we can see that we have the results we expect. False, false, and then a false, false, and then a false, false, and then a false, true, and then a plain true, and then again a false, false. And we have a result of 2. So I will remove the console logs. We don't need them. This is totally operational. This is the huge input, and let's just run our code for the huge input. And we got back the results. The results is 967 out of the thousands are overlapping. To be honest, I'm not too confident that this is the right answer. But let's see, maybe it is. Yeah, it's not. Let's return to day 4. Okay, I spoke too soon. Let's see what... Oh, somebody is being stupid. If you remember, we changed the size of the map instead of 1,000 to 10, which was great for the small example because the small example was using numbers up to 10. The large examples uses numbers max to up to 100. So we had basically an error, a sizing error in our input. Let's try this again. And now the result is a flat out 1,000, which just cannot be correct. That would mean that all of the inputs, and there is 1,000 of them, are full overlaps. And let's actually see. No, at least this one is not an overlap. This one is an overlap. This is not an overlap. This is not an overlap, and so on and so forth. So why does the third one get marked as an overlap? It's 1,000 max size. Again, I made a boo-boo removing the console logs. Run it once more. And now we have a number that looks like it might be correct. 536. One way to find out. 536. And that is the correct number where wild goats are closer to collecting enough starfruit. Let's see what the second part is. It seems like there is still quite a bit of duplicate work planets, and I would like to know the number of pairs that overlap at all. Is it possible that the second part is actually easier than the first? In our case, for our algorithm. Um, 2, 3, 4, 5, 5, 7, 7, 9 overlap. overlap, overlap, overlap. Yeah, we actually discussed that. So let's have the small input and see the exact same code for the second part. But instead of counting, making sure that there are ones and two, we basically just need to find three. If there is a single tree, that means that we have an overlap. And basically we can just say this. If there is a tree, increase the counter. And this would have been quite a difficult thing to get the expressions just right, which should be bigger or equal to which, and so on and so forth. But now for the small input, we should be able to see the value for the second part. And we have it here. It says that we have two totally overlapping and four partially overlapping. That's great, and that is the value that we were looking for. Let's see if we get lucky this time with the full input. Let's just start it. And it says the full result is 845 partially overlapping. This will be higher than the completely overlapping, so it might be even the correct number. And that's the right answer. We completed day 4. We have 8 stars here. Let's see what our advent calendar looks like. Well, yeah, it is a jungle. So developers, that's it for today. The code will be available on GitHub. This is not a standard way to solve things with intervals, but we abused the fact that there are not too many sections or whatever these were called to basically run a full simulation, and we intentionally run the simulation about 10 times what it should be, but as you can see the processing time is few milliseconds. In this case this is okay. Sometimes it won't be. So make sure that you know your data when you're writing your code. This approach only worked because I knew my data. It will not work in general case, but we don't need it to work in a general case. We needed to solve the task, and the task is solved in some sensible time. So, bye and see you tomorrow.